In this chapter we're going to be looking at sampling distributions. Now this will be still a review of some of the things that we've looked at with the normal distribution, and we'll still be using the normal table, so make sure you have your calculator and your normal tables out to work through some of these examples. Specifically, when we're working with sampling distributions, we're going to go over parameters versus statistics, which we have talked about these a little bit before. The law of large numbers. We'll talk about different sampling distributions. We'll be focusing on the mean and population proportion. So again, sampling distribution of the sample mean. We'll talk about the central limit theorem, and then the sample proportion as well, like I stated. So to get started, let's go ahead and talk about the parameter versus a statistic. Now if you recall from previous lectures, we defined a parameter and a statistic already, but let's do a quick review. A parameter is a number summarizing the population. So we should also probably talk about what a population is. And again, a population is the entire group of individuals that we're trying to get information about. And usually we can't use a census to absolutely observe every single value, so that's why we take a sample. And from this idea of a sample comes a statistic. Now, as a parameter is a number summarizing the population, a statistic is a number summarizing a sample. So how can you remember? This is a good fill-in-the-blank type of question. What is a parameter? It's a numerical value that summarizes a population. Well, if you notice here, both of these, parameter and population, start with the same letter P, and over here statistic and sample start with the same letter as well. So that's kind of a good mnemonic device to remember. Parameter goes with population, statistic goes with sample. Now that we have this idea of a parameter and a statistic, we can also talk about this in terms of a population and a sample. Now remember, population is the entire group that we're interested in finding about information on, and then a sample is usually a subset of the group. So all the values from a sample have to come from that particular population. So now that we kind of know what we're up to, we are trying to use a statistic, which is based on a sample, to estimate a parameter. Because again, a parameter is a good estimate or a good measurement of a value from a population. We can't come up with that value from the population because we can't do a census, so we use a statistic to estimate it. And again, this is a good type of test question as well. A statistic is used to estimate a parameter. Parameters don't estimate statistics. It only moves in one direction. Well, one of the ways that we can use this idea of parameter and statistics is with the law of large numbers. Now the large numbers that this law is referring to is basically our sample size. So the law of large numbers basically says, as the number of randomly drawn observations of sample size n increases, we can get a lot of good information about the population from which it was drawn. Now the law of large numbers has important implications in gambling, of course, because we would talk about whether a casino can make money or not, and also with the insurance industries, and not just health care but auto life insurance as well. So let's go ahead and write out the law of large numbers and then talk about its implications. So again, as the number of randomly drawn observations, and the number here is referring to our sample size n. N is sample size, lowercase n is sample size. And a sample increases, so as this number n increases, and basically that means our samples are getting larger and larger. So the implication here is instead of randomly choosing 2, we might randomly choose 20 or 30 or 40 or 50 from a population. And what makes sense here is the more we gather from a population, the more information we're getting about that population, the more accurate our estimates about that population. So that's really what the law of large numbers is going after. But there's two implications that come out of this. The first one is the mean of the sample. So we pull a sample of size n and we find its mean, which is x bar. This value of x bar will get closer and closer to the true population mean as n gets larger and larger. Now this is for quantitative random variables. Things like height, weight, GPA, etc. The second implication talks about the sample proportion. So the sample proportion, and this is a new notation for us, is called p hat. So we have p hat here. So the sample proportion gets closer and closer to the true population proportion Now our population proportion is represented with this p. So again, sample proportion is p hat, population proportion is p. Now in this particular case, I'm not talking about a quantitative random variable. Here I'm talking about a qualitative random variable. So these would be things like hair color, country of origin, things like that. So again, as our sample size gets larger and larger and larger, my statistic that I'm using, whether it be x bar or p hat, gets closer and closer and closer to the actual true value of x bar or p hat from the population. Now the way that this looks graphically is pretty interesting. This first graph that we're going to look at represents case 1 up here when we're talking about the sample mean. So for this first one, we're talking about sample mean, x bar. So let's try and interpret what this graph is saying. First of all, on the horizontal axis and our x-axis, this gives me our sample size n. So this would be a sample of size 1. This would be a sample of size 5, and then I'd calculate the average. This would be a sample of size 10, then calculate the average. Sample of 5,000 and calculate the average. And what this is saying is these values are pulled from a population that has a mean of 25. So this value of 25 is the true mean of the population. So what's going on here then is we're seeing, boy, if you just select one member of the population, you're not going to get a very accurate estimate. If you select 5, it looks like you do a little bit better job. If you select 100, man, you get really, really close to that true population mean. And then after we get a large enough sample size, that just bounces back and forth across from that true mean. Now over here we have the sample proportion. Now again, the symbol for the sample proportion is p hat. So if we look at this proportion, this is kind of our number of times that we're going to do the experiment. In this case, we're flipping a coin, so it's number of tosses. So if we toss a coin and we're looking at the proportion of heads, it looks like on this first toss I got exactly 1 head, so the proportion of heads is 1. Now as we move on and I toss the coin 10 times, the proportion of heads looks to be a little bit more than 0.5. Well, if it's a fair coin, we would expect my value for p to equal exactly 0.5, and that's what this line is. Now as we see here, as we toss the coin 100 times, 500 times, 1,000 times, etc., we get closer and closer to that true proportion, that true population proportion. So that's the law of large numbers. Now the law of large numbers helps us make a lot of different implications, from sampling distributions to the central limit theorem. So the next thing we're going to look at are sampling distributions. So a couple quick notes. When we're talking about a sampling distribution, what we need to do is we need to understand that when I sample different groups of, let's say, size 10 from a population and calculate the average of that sample, the average is going to vary from group to group. I'm not going to get the exact same value out of each one. So different random samples taken from the same population will give different statistics. But the deal is there's a predictable pattern how this works in the long run. So what the implication here is a statistic computed from a random sample is a random variable, and because it's a random variable, it has a shape of a particular distribution. And so that's what we're talking about with a sampling distribution. So to review these ideas again, different random samples taken from the same population will give different statistics. So if I have my class and I take a group of 5 students and calculate their GPA and another group of 5 students and calculate their GPA, I'm going to get different values or different statistics. But there's a predictable pattern in the long run, meaning I know that they're going to go toward a particular value from the population. So a statistic that is computed from a random sample is a random variable in and of itself. And then we talk about the sampling distribution of the statistic is the probability distribution of that statistic for samples of a given size n taken from a given population. So what that means is I take all these averages that I calculate on all these groups of 5 from my class, and I note them and I record them, and I get a sampling distribution. I get possible outcomes listed with their corresponding probabilities, and that will give me a histogram, and then I smooth the histogram, and hopefully that histogram will have a shape that's something normal or another type of distribution that I can use. Now when you're randomly sampling from a given population, the law of large numbers describes what would happen if we took samples of increasing size n. A sampling distribution describes what would happen if we took all possible random samples of a fixed size n. So this sampling distribution would talk about what would happen if we took all possible values. But we can't take all possible samples of size, let's say 5 from my classroom, because there's a lot of them. So both of these, the law of large numbers and a sampling distribution, are conceptual ideas that have a lot of really good practical applications, and we rely on the properties of these distributions to be able to talk about how to find probabilities of the sampling distribution. So to get started, let's go ahead and talk about the sampling distribution of x bar in particular. We'll also talk about the sampling distribution of p hat, but we'll start with x bar. Now again, x bar is the sample mean. So the mean of the sampling distribution of x bar is mu. So the way this looks is there is a mean of the sampling distribution of x bar. And when I find that true mean by taking all the possible samples of size 5 and completing those averages and then taking the average of the average, mathematically it'll actually equal the exact population mean, which is really cool. Now there's no tendency for a sample average to fall systematically above or below mu. So what ends up happening is some values will be too high, some will be too low, some will be spot on, but there's really no way to predict that particular pattern. Now what it also ends up happening is it doesn't matter if your population distribution is skewed, right skewed, left skewed, bimodal, etc. This is a characteristics that will always be in place. What we say there then is x bar is an unbiased estimate of the population mean mu. So on a test or a quiz we might say x bar estimates mu. And we've already talked about some stuff like this before, because a sample estimates a parameter, or a statistic estimates a parameter, a sample estimates a value from a population. So those are all common ideas. So now we can also talk about the standard deviation. Now with the standard deviation of the sampling distribution, you might think, oh, it's probably exactly the same as the standard deviation of the population itself, but that's not true. As it turns out, the standard deviation of the sampling distribution of x bar is sigma, which is the population standard deviation divided by the square root of n. N is our sample size, of course. Now the standard deviation of the sampling distribution measures how much the sample statistic x bar varies from sample to sample, because sometimes it'll be too high, sometimes it'll be low, sometimes it'll be just right. So this value of sigma over root n talks about how much it varies from sample to sample. Now what the upshot here is, because I'm dividing by root n, averages are less variable than an individual observation. So after we've written everything out here, basically this boils down to one particular distribution that we want to talk about. So all of this that we've talked about boils down to the fact that x bar is distributed normal with mean mu and standard deviation sigma over the square root of n. So that's what this is coming up with. Now this is true for my underlying distribution is of my x values to be normal. My x bars are also distributed normal. But if my underlying distribution is, let's say, right skewed or left skewed or not normal, this approximation x bar is only approximately normal mu sigma over root n. But as n gets larger and larger, this becomes a better and better estimate. So important thing to remember here, x bar is distributed normal if x is distributed normal, and also x bar is distributed approximately normal if x could be right skewed, left skewed, or from a different type of population. So let's go ahead and talk about what happens if my x values, my population values, are normally distributed. So for normally distributed populations, so my values of x, they come from a normal distribution with mean mu, standard deviation sigma. So these are my values of x. The mean is at mu here. So this is what we say when we talk about the underlying distribution is normal. Now what we want to talk about then is pulling samples of size n from this population. Now when we pull values of size n from this population, what's going to end up happening is I find the average of each of those values then. So here, x bar, and again these are based on samples of size 10, x bar is distributed normal with mean mu, standard deviation of sigma divided by root n. So what ends up happening here is the shape of this particular distribution of the x bars, not just the x's but the x bars, is still centered at the mean. But notice as n gets larger and larger, this overall fraction gets smaller and smaller, so the spread or the variability, it's not a very good graph right here, the spread or the variability decreases. So we can see this top distribution has a lot of spread centered at the mean. This bottom distribution has very little bit of spread, but it's still centered at the mean. So that's kind of what we want to talk about here. So let's look at a particular example of a random distribution. So let's say x is distributed normally with mean mu equal 25 and a standard deviation equal to 7. Then what we do is we try to take random samples of size 10 from this population, and we do this over and over again. So our first random sample of size 10, I'll calculate x bar. Our second random sample of size 10, I'll calculate x bar. Our third random sample of size 10, I'll calculate x bar. And I do this over and over and over again. Well, what ends up happening with these values, I can talk about the shape of their distribution is also normal. And the mean of this distribution is also going to be 25, and its standard deviation is going to be my old standard deviation 7 divided by the square root of my sample size. So I should have tried to fit that on one line. X is distributed normal, mu 25, sigma 7 over root 10. So that's what ends up happening here. So first of all you have something like this, and then I can talk about how it turns into the sampling distribution or the distribution of the sample mean. Now, all the same rules apply to this distribution, like the empirical rule, the 68, 95, 99, 7 rule, the normal tables, all those things still apply. So let's go ahead and look at an example where we're looking at some data and trying to draw some conclusions from it. So an example the book gives is it talks about the body length, excluding the tail, of deer mice. And so I'm going to talk about L for length. So length is distributed normally with mean of 86 millimeters, standard deviation of 8 millimeters. Then what we do is we take a random sample of 20 deer mice. When we take a random sample of 20 deer mice, then the conclusion that I can draw is the average length, which is L bar, is also distributed normal with mu of 86, population mean of 86, but my standard deviation changes. So here my standard deviation of x bar, and I should be using this x bar notation, just so to clarify up here, so you understand that there's a difference between sigma and sigma x bar. Let me see if I had any more of those. That one's good. I think we got them all. And again, the notation is understood, but this is just to clarify the difference between the sigma, actually that one shouldn't be there, the sigma from my distribution of my population, and the sigma x bar, which is based on the sampling distribution of the mean, and that would be equal to 8 over square root of 20. And I'm not going to find the square root of 20 or reduce this to a decimal. I'm just going to leave it as 8 root 20. So the sampling distribution of the average length is distributed normal with a mean of 86 and a standard deviation of x bar or L bar of 8 divided by the square root of 20. So that works out pretty well, and then once we find those pieces of information, then I can start again using my normal tables and trying to figure out some proportions and population values as well. So the question is now, how do we normalize from a sampling distribution? So standardizing a normal sampling distribution. Now if you recall, we already have learned how to standardize, but we standardize with a sample of basically size 1. We looked at individual observations. So previously, we said z equal x minus mu over sigma. But again, that was just a single observation. Now that we have this sampling distribution, z will equal x bar minus mu still, divided by not sigma, but sigma over root n. So the changes are here. Instead of just x based on one observation, I'll have x bar based on a sample of size n. And here, instead of just sigma, I now have sigma divided by square root of n to account for the fact that the variability decreases here. So for this distribution, I can look at a couple different examples as well to talk about what's going on with the shape. So I have a distribution, x bar is distributed normal with some mean and a standard deviation of sigma over root n. And then what happens is I standardize that value, x bar minus mu, sigma over root n. And be careful with your calculators here that you don't mess up this problem in terms of order of operations. Find that denominator clearly. And this value of z then is distributed normal with a mean of 0 and a standard deviation of 1. And now we're back to our normal table. So that's nice. It looks very familiar. Now again, sigma is the standard deviation of the original population, so that's where that value comes from. So let's go ahead and look at an example where we're trying to take this information from a population, change it into information about the sampling distribution of the mean, and then actually use some values from your normal tables. So let's go ahead and write out our example. So for our example, we're looking at blood, and in the blood we're talking about a condition called hypokalemia, and it's diagnosed when blood potassium levels are low. Now we can't just say low, we have to give it a specific number, so we're saying anything that's below 3.5 would be the value that we would talk about. Now what we're going to do is assume that we have a patient whose measured potassium levels vary according to the normal distribution. So we could say their levels are represented by the random variable x. So x equal potassium levels. And this is according to a patient, of a single patient. So we're not looking at samples here yet. Then as it turns out, x is distributed normal with a mean of 3.8 and a standard deviation of 0.2. Okay, and so this is all from the given information. Now what the question that we want to answer here then is if only one measurement is made, so a single measurement is made, what's the probability that this patient will be misdiagnosed, not diagnosed, but misdiagnosed, with hypokalemia. So what we're trying to talk about then is trying to set up a probability distribution, drawing our table, using our normal curve, etc. So the first thing I'd like to do is go ahead and draw up a normal curve. Now we talk about this normal distribution and we want to talk about what its mean is. Well, the mean of this normal distribution is 3.8. So this value of 3.5 or below, well, we know 3.5 is right here. So again, we want to know what's the probability that they'll be misdiagnosed. Well, if we talk about this up here, 3.5 or below is a misdiagnosis. So the area that we want to find will relate to that probability. This is basically the probability or the proportion that will have a misdiagnosis. They do not have hypokalemia. Sometimes potassium levels drop, but they do not have that condition. Okay, and sometimes they go back up. And so again, you have that variability that's taking place here. Well, we want to figure out what's going on here with these values of x. So I want to standardize these values. When you standardize the mean, it becomes 0. And then I want to figure out how far this is in terms of standard deviations below the mean. So the distance from 3.5 to 3.8 is 0.3. So that again, that total distance is 0.3. And then I divide that by 0.2 because that's my number of standard deviations. And because it's below the mean, it's going to be a negative. So this is negative 1.5. Now let's go ahead and look at this in terms of probability statements. We're talking about the probability that x is less than 3.5. Okay, well, when we standardize, we would have to look at z equal x minus mu over sigma. So this means z would equal 3.5 minus 3.8 over 0.2. Negative 0.3 divided by 0.2. I get z equals negative 1.5 here, just the same as I did when I logicked my way through it. So this statement rewrites to the probability that z is less than negative 1.5 standard deviations below the mean. Now to figure out what this equals, remember our normal tables give us the area to the left of a particular point, so I would look up negative 1.5 in my table and I would get 0.0668. So that's about 7% or 6.68%. So again, the first question asks about a single measurement and therefore relies on the population distribution that we have listed up here in the normal area. Now the next question we're going to ask, it asks about the averages from 4 different measurements, and so that way it's going to have to rely on a different shape of a distribution. So again, make sure you understand which type of problem you're working with. So just as a quick note, this area is 0.0668. So second question. If instead measurements are taken on 4 separate days, what is the probability of a misdiagnosis? So suppose measurements are taken on 4 separate days. So I would take these 4 days of measurements and then I would find the average of those. Find the probability again. Of a misdiagnosis. Okay, so let's go ahead and review. We have x is distributed normal, mu in this case was 3.8, sigma is equal to 0.2, then x bar, based on the fact that I have a sample of size 4 here, is distributed normal as well with the same mean. But now my standard deviation will change. Sigma of x bar will equal 0.2, my old sigma, divided by the square root of my sample size, divided by square root of 4. So x bar will be distributed normal, mean of 3.8, standard deviation of the averages will be 0.2, and then the square root of 4 case is 2, so when I divide that out I get 0.1. So now when I want to find the probability of a misdiagnosis, I again draw the curve, but instead of using the value for my mean here of 3.8, my standard deviation has changed, and this distribution over here is not the x's, but it's the x bars. Now when I talk about the distribution to the left of 3.5 being shaded right here, now it's not as many standard deviations away. So when I standardize this, again the mean standardizes to 0. The distance between 3.5 and 3.8 hasn't changed. That's still 0.3. But now instead of dividing by 0.2, I divide by 0.1. So when I divide this out, I get 3. Now don't confuse these scales. This is x bar and this is z. So now if you grab your graph, and this should be a -3, sorry. Now if you grab your graph of the normal tables and I look up -3, I get for this particular area 0.0013, which is less than 1%. But let's go ahead and write out all that information down here. So I'm talking about the probability that the sample average, when I have a random sample of size 4 is less than 3.5, is going to be equal to the probability that z is less than, and I'm just going to standardize right here inside my problem this time. This is equal to the probability that z is less than -3 here. Again, you can calculate that out, which is phi of -3. And if you look this up, you get 0.0013. Okay, so again, very, very small probability. Now, why the difference here? Why was this 3.5 didn't change, but the standardized value changed? So up here, notice, this used to be 1.5 standard deviations below the mean. Now it's 3 standard deviations below the mean, because our sampling distribution variability gets smaller as my sample size gets larger and larger. So that's an example of where we can talk about the sampling distribution and applying it to the normal tables. Next thing we're going to talk about is the central limit theorem. And the central limit theorem is very important because it allows us to basically talk about an underlying distribution that's not normal. What if my underlying distribution wasn't normal? What would I do? So let's go ahead and look at the central limit theorem and draw any conclusions that we can from the central limit theorem. And as with the law of large numbers, the central limit theorem is based on sample size as well. So let's see what the central limit theorem says. First of all, when you're randomly sampling from any population, and this population has a mean mu and a standard deviation sigma, when n is large enough, our sample size is large enough, the sampling distribution of x bar is going to be approximately normal. So I have this tilde with a dot above it to represent approximately normal, with the exact same mean, but now my standard deviation again is sigma over the square root of n. Now what's the difference between this and everything we just did? Well, everything we did before, up here it says when randomly sampling from any population, before we said randomly selecting from a normal population. So now we're saying, you know what, it doesn't matter. It could be right skewed, it could be left skewed, it could be binomial, it could be bimodal, it could be any of those things. But this is saying it doesn't matter. When I randomly select large enough sample size, the distribution shape of my sample means is going to be approximately normal. Now, of course, the thing that I notice here, it says when n is large enough, right here, when n is large enough. Well, what does that mean? What does large enough mean? Well, as it turns out, the larger the sample size, or the larger the value of n, and again, n is our sample size, the better the approximation of normality. So the larger our sample size, this actually gets closer and closer and closer to a perfect normal distribution. Now this is very useful when we're talking about inference, when we're trying to take something about a sample and infer it to a population. Many statistical tests assume normality for the sampling distribution, and the central limit tells us that if the sample size is large enough, and we'll talk about what large enough means here pretty soon, we can safely make this assumption even if the raw data that we're looking at don't appear to be normal. So this is a very powerful statement because again, we assume normality in a lot of different types of cases. So next, what does large enough n mean? So let's go ahead and look at how large a sample size is needed in order to apply the central limit theorems. So how large a sample size do we need? And of course, the bigger the better, but a lot of times there's a cost involved in collecting data. So how large of a sample size is needed? It depends on the population distributions. More observations are required if the population distribution is far from normal. So our sample size n has to get larger and larger, and that's what we say when we say more observations. That means sample size has to increase. More observations are required if the population distribution is far from normal. So the further from normal that the population is, the larger our sample size is going to have to be. And the closer that our population is to normal, the smaller our sample size is going to have to be. Now, in general, these are some rules of thumb here. A sample size of 25 or more, so n of 25 or more, n greater than or equal to 25, is generally enough to obtain a normal sampling distribution from a skewed population, even if there are mild outliers in the sample. So n greater than or equal to 25 is generally enough to obtain or to apply the central limit theorem from a skewed population. Even if mild outliers are in the sample. So from a skewed population with mild outliers. And we know how to calculate outliers. Now, if I have extreme outliers, then I have to have another case involved. But a sample of size 40 or more will typically be good enough to overcome an extremely skewed population and some mild outliers, but not extreme outliers. If we have extreme outliers, we need an even larger sample size. So n is greater than or equal to 40 from not just a skewed population, but an extremely skewed population. And again, with mild outliers. Extreme outliers, I'm going to need an even larger sample size. Now, in many cases, a sample size of 25 isn't a huge sample. So even from a strange population distribution that we don't know much about, we can assume a normal sampling distribution of the sample mean and work with it to solve problems. Now, I've seen a lot of other rules of thumbs like 30 and 32, so I think 25 is a pretty liberal estimate. But the rule of thumb here is the larger the sample size, the more accurate your estimation. Now, there's no one formula that says which is the exact best number. So what we can talk about here again is the larger the sample size, the better, and it appears that 25 is kind of a low end point to make any assumptions about normality. So everything we've talked about so far has been related to the distribution of the sample mean. Next thing we want to talk about is the distribution of not the sample mean, but the distribution of p hat, the sample proportion. So p hat is distributed approximately normal with a mean of equal to whatever this value of p is. Standard deviation is going to be p times 1 minus p. Sometimes you'll see that written as pq over n, and all of this will be square rooted. Now what happens is this is the best approximation if n is large and p is not too close to 0 or 1. So that's something that you'll also need to look at and account for. Now what we would like to have happen here, if this is a good approximation, then NP is going to be greater than or equal to 10, and also n times 1 minus p will be greater than or equal to 10. So this is a good approximation if these two cases hold true. Now what is n? N is the sample size, and then also what is p? P is the probability of a success. Now a success could have any type of connotation, meaning a success could be a person that's diabetic. A success could be you're an engineering major. It basically just means what we're interested in counting. So let's go ahead and look at an example to finish off this particular discussion on sampling distributions. So the frequency of color blindness in the Caucasian American male population is about 8%. So this 8% is the probability of being colorblind. That is a success to me because that's what I'm interested in counting. So the probability of success is 0.08. Now 125 is my sample size because we are going to take a random sample of 125 people from this population of Caucasian American males, and we're going to try and determine what is the probability that 10% or more in the sample are colorblind. So let's go ahead and get started trying to summarize all this. First of all, C, the proportion who are colorblind, I'll just use C for my random variable, is distributed approximately normal with the mean of 8%, 0.08, and a standard deviation of 0.08 times 0.92 divided by 125, and this is square rooted. So if we calculate out these values, I get mu equals 0.08. And then for my standard deviation, again, please be careful on how you calculate these. 0.08 times 0.92 is 0.0736. Divide that by 125 and you get 0.0005888. Okay, then what we want to do is we want to take the square root of that value. Now when we take the square root of that value, I get sigma equals 0.02426, and I'll round that to 3. Do not over round at this point because you will get wrong answers, so don't over round. Now when we're working through this, the next question is this a good approximation? Well, let's check to make sure that NP is greater than or equal to 10, and also that n times 1 minus p is greater than or equal to 10. So the way that this would work is n is 125, p is 0.08, and if I take 125 times 0.08, let's see what I get here. We get 125 times 0.08 is 10. So this is greater than or equal to 10, so that's good. Now n times 1 minus p would be 125 times 0.92. Okay, and that should be equal to the complement of that. So that should equal 115, and that's greater than or equal to 10. So these are good values to come up with an approximately normal distribution. Okay, now let's draw out our picture. So this is the sampling distribution that's approximately normal with a mean of right here at 0.08. So these are our values of C. Now what we're looking for here is we are looking at finding the probability that 10% or more in the sample are colorblind. Well, 0.08 is 8%, here's 10%, 0.10. So I want to know the proportion that's 10% or more. So right away I notice that this better be less than 50% when I get all done. So we go through the same process as before. I standardize the standard normal random variable. The mean standardizes to 0, and let's look to see what's going to happen here. To standardize here, I'm going to take my observation P, subtract the mean, which is 0.08, and divide by the standard deviation, which was 0.0243. So let's go ahead and calculate what that is. So again, 0.1 minus 0.08 divided by 0.0243, and I get 0.82304. But my standard normal tables are really only good to 2 places past the decimal, so I'm going to call that 0.82. So this says I'm 0.82 standard deviations above the mean. Now if you look up 0.82 in your tables, you are going to get this area over here to the left. So we need to make sure we remember to take the complement to find this area on the right. So again, look up 0.82 on your tables and you get 0.7939. And then if we take 1 minus 0.7939, because I'm trying to find the area to the right, I end up with 0.2061. So about 21% or 20.61% of the population has the probability, if we scoot back up here to look at the question, what is the probability that 10% or more in the sample are colorblind? It looks like it's about 21%. Now in terms of writing this in probability statements, we're talking about the probability that the proportion of colorblind people in this particular population is greater than 10%. So we can use 0.10 to represent that. When I standardize it, it becomes z greater than 0.82, because that's about 0.82 standard deviations above the mean. Looking up on my table, that's 1 minus phi of 0.82. If I look up 0.82, I get 0.7939, which is 2061. So again, this makes pretty good sense when we're using those normal tables. It just looks like a big puzzle again. So the important thing to remember here is we're still standardizing. We still standardize by taking my observation minus the mean divided by the standard deviation. But what's changed here is how we calculate those distributions and whether that sample size condition has been met.